Welcome to the last topic that we're going to talk about in this course, and that's going to be arrays. Arrays themselves, I wish we had much more time to talk about them. They are probably the most important data structure in computing science. Unfortunately, you need a lot of knowledge of how simple variables can store information, how routines work in terms of flow of control for looping and making decisions, understanding natural program flow, which is that sequential flow, before you could even consider looking at arrays. So it's a very strange circumstance that although they're so important, arrays themselves require so much more knowledge in order to just do simple manipulation. I've seen other topics which introduce arrays much earlier, and it ends up causing a lot of confusion because the limitations of arrays are not apparent until you actually start using them. So that's why this course treats them as the very last topic, yet in a way, they're the most important topic in computing science. So what are arrays in general? Well, arrays, if we can just look at them, you can think of it as just an ordered list of values. And by ordered list, it means that the value itself of 79, 87, 94 is not as important as the order that they take. That the first value in the list is 79, the second one is 87, the third one is 94, and so on. And that order is maintained. Nothing changes that order. You can change the value within here, but the order is still always maintained. And that's one of the key aspects of arrays. It's an ordered list of values. And the order is whatever you want it to actually be, but it is defined by this 0, 1, 2, 3. And we'll talk about what the ordered itself actually is. Now, other languages treat list as a very special term. Java has that definition as well. Later on in programming, you will see collection classes, list classes, order classes, where you can keep something always in sorted order. An array is not that. An array itself is very, very simple. So we'll get back to the definition of all of these, but if we look at a list here, there we go. What is an array itself? An array reference points to a contiguous block of memory. So what does that term contiguous mean? A contiguous block of memory. It doesn't refer to the term continuous, which is something that keeps going on and on and on, and then stops for some special circumstance. Contiguous is a different term, and what it means is it means unbroken. So if you look at the list here, it's all integers. It means it's unbroken. There's nothing in the middle here. There's not a double value or some sort of string or anything else in the middle. There's none of that. If we go back to the original list we were looking at, you see that the first value here is 79, followed by 87, 94. They all happen to be the same type. In this case, they're all integers. The index, which is the 0, 1, 2, when that's how we refer to each element, that is unbroken. It doesn't go 0, 1, 3, 7, 52, 2, 9, 12. This order is what we talk about when it's referred to as contiguous. Now, what we're actually referring to is the block of memory. So we've looked at computer memory before. In terms of describing stuff just gets thrown into computer's memory. We've never really thought about one thing next to another. Arrays stipulate that things must be one next to the other. So if we look at an array declaration, we'll be looking at a number of them. If you look at this declaration right here, what it says is I'm going to create an array of integers, and that's the notation that we use. I'm going to call it scores. That's the name of this array. And it's going to be defined as new block of memory of 10 integers. So what Java will have to do, what Java and the virtual machine and the operating system, what they'll all have to do is find a block of memory that has 10 integers unbroken together. And that's what an array means, a contiguous block of memory. So we're going to find the first integer, and there had better be 10 integer spaces after that, and that gives us our block of 10 integer values. So how much memory is that? Well, an array itself, and this is part of it being a fundamental aspect, is the number of the elements multiplied by the data type of each element. So in this case, it's a block of 10 integers, so it's a 10 element array of type int. We know that an integer is 4 bytes big, so each integer is going to take up 4 bytes of memory, which means this array here called scores is going to eat up 40 bytes of memory. Now, in the circumstance, let's say the virtual machine is eating up a lot of memory, and Java is unable to find that 40 bytes of unbroken memory. It's not going to find 10 bytes over here and 10 bytes over there and find the remaining 20 bytes somewhere else in memory. No, it has to be 40 bytes from beginning to end, unbroken. In terms of addressing, if Java can't find that, this program will probably crash. You'll get an exception error, maybe some sort of stack dump, meaning that the program just couldn't function. This is how important arrays are. It's this unbroken contiguous block of memory. Now that contiguousness actually plays a very important role as to how we manipulate and access arrays. But for right now, just keep in mind that whenever we declare an array, when we specify its size, the Java virtual machine needs to find that block of contiguous memory, and that's very important. So now let's get back to not talking about contiguous, but talking about an array itself. So here's our original array that we looked at. So we call the array scores, and scores is going to refer to all the values. So we don't have to specify each individual value, we can just call it scores. In the very same way, when we declare an integer variable, we call the integer, we just call it age. We don't refer to the value inside that variable, we just say age. And Java knows that that's memory location, that's what we're referring to, and it happens to have maybe a 17 or a 12 or a 32 in there. That value is what we refer to as age. So the array itself is going to be the very same thing. We're going to call this array scores. Now within this array, here's where we can actually store our information. We can store one or more element values. Now we have to define how many values are going to be in this array, and that's going to be part of our declaration, which we'll look at in a moment. But we know that our array is going to have a certain number of elements in it. And in this case, well, it's got 10. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 10 elements in this array. So the size of the array is n. And the index, what the index value is, it's the position in the array. And you'll notice that we start counting at 0. Everything in computing science starts at 0. That's just the way it is, and that's how we've been looking at strings. So when we use the charat method for a string, we're trying to find a particular character at a particular position. We've used the term index, and the very first character in a string is at index position 0. This is now probably going to explain to you how a string stores its characters. It stores them in an array. So when you create a string object and you give it a value like Bob Smith, the capital B is the first letter in that string, what we have is a string storing an array of characters. And that's actually how the string class stores the character information within itself. It's using an array. So we looked at this one. We've got each value at an element position in the array. So it's called scores. The very first element at index 0 is going to store 79. The second index value here is a 1, and that's pointing to the second element, 87, and so on. Now, one of the key things about arrays, especially in Java, is that all the elements are of the exact same data type. And that's actually extremely important for how Java treats arrays. Other languages can have what we call variable typed arrays. and which means you could have the first element be an integer, and the second element being a character, and the third one being a double, and then a Boolean, and maybe a string reference, and so on. Java does not support that idea of variable typed arrays. An array in Java is going to be the exact same type for every single element. And again, that comes back to it being a contiguous block of memory. Every element is going to have the exact same byte size. So that we know, if we looked at it over here, that this array called scores has 10 elements. They all happen to be integers, which means Java knows exactly how much memory to try and find in order to store these values. So this is why Java has this idea that an array itself is going to eat up a block of memory. It's going to be a certain size because each element within there has a certain byte size as well, and Java can reference them very easily. You can think of an array actually as a collection of variables. So in this case, we've got 10 integer variables, one right after the other in memory. We don't have to call it v1, v2, v3, all the way up to v10. We just say that this is going to be an array. We're going to call it scores, and we're going to be able to access each individual in here. This is also an advantage. If we wanted to declare our array instead of size 10, we wanted it to be 100 or 1,000 or 1,000,000, you just specify the size and you let Java and the virtual machine and the operating system find that contiguous block of memory and you can assign it. We don't have to declare each individual variable within that array. We just declare the entire array and Java finds that memory for us. And it is one of the key features of arrays. It's of a size that is not predefined. The element type, the fact that it's an integer, that is defined. But how many of those integers? We don't know until we actually run the program, and Java needs to find that memory. So how do we reference the array in terms of a name and identifier? Well, you can see that we just called it with a name. So we just called it scores. Just like any other identifier in Java, it follows the exact same rules. So we can look at how we reference it. We're using the square bracket notation. For the very first time, we're using the square brackets as something which is an aspect of the program. Previously, we've only seen it with public static void main string args. We see the square brackets there. We're going to come back to that. It's very important. But that is the first time you saw the square brackets, but we never use them in any other context. Java knows that square brackets mean array. So if we look at this, scores2 refers to value 94. If we go back to our memory over here, we look at index 2 has the value of 94 in it. So that would be this very similar syntax as us declaring an integer, calling it score number 3, so score 3, and assigning it the value of 94. But in this case, we can just reference it this way. We just say we want to reference the scores element at index number 2, and it has the value of 94 in it. So the syntax is actually really, really simple. There's nothing too special about it except for indicating with square brackets which element in the array you want to reference. This is why arrays themselves, once you start using them, you continue using them. They are so useful in terms of programming. In a way that if you wanted to declare 5 integers, instead of declaring integer number like a v1, a v2, a v3, and so on, you just declare an array of size 5 and then index into each element just like you would in a program that's referencing each individual variable. It's extremely useful. So you can look at arrays in different ways though. This is the classic horizontal view of an array. Now it just means that we're starting at this memory location over here and we proceed to the other elements subsequently. But memory itself doesn't follow this structure. Computer memory is organized in terms of circuits and memory addresses. that is not something we can easily visualize. So you can look at an array as being horizontal like this, or you could also look at it as being vertical. It doesn't matter. The only key feature of the array is that it's a contiguous block of memory. So all the blocks are together, whether they're horizontal or whether they're vertical. So arrays just have that idea of a contiguous block of memory where each element is of the same type. Once you've got that, now you know everything you really need to know about how an array is stored in memory. That's about it. So let's take a look at this example here, just to reinstate that idea of the contiguous block of memory. So we've got our array called scores. We've declared it with this notation. We've told Java, I'm declaring a new thing here called scores, and I'm going to use the syntax int with square brackets. There's nothing inside the first set of square brackets. That is just a notation to tell Java that you're creating an array. You're not creating an integer variable. Scores is not an integer variable. It's going to refer to an array of integers, and this is the syntax that we use. So Java knows that this is not going to be an integer variable. It's going to refer to an array of integers. Now, how much memory does Java need to find? Well, it needs to find 10 of these integers. So we've used this idea here of declaring an integer. The square brackets again tell Java that this is an array, and now we indicate how many of those integers, how many of that block of integers do we need to find? In this case, we need to find 10 of them. Now, what does scores actually store? Well, as it says down below here, and you could intuit that just from the word new. When we've used scanner, scan is assign new scanner, or random is assign new random. The new keyword we know means return back a memory address. And we see the assignment statement, so clearly scores is not going to store an integer as a simple integer. It's going to store a memory address of where this array is because of this new operator. So that is why we introduced this idea of objects and declaring them with the new operator. We needed to understand how memory is referred to as a reference. So scores itself is not the array itself, it's a reference to where the array is. So how does it look? Well, this is how it looks in memory. So scores itself, we've got it over here. It is the memory reference to where this array is. So scores is going to store a memory address. So the memory address itself could be x5f, for example. Wherever this is in memory, it doesn't really matter, but it's going to indicate where the first element is in memory. So when Java declares this array of 10 integers, and it's going to make it a contiguous block of memory, it's going to return the address of the very, very first element in the array. And that is what gets stored over here. It doesn't store the value of what this array element has. That's just going to be a regular integer. For example, 79. It's just a value that we're storing in the array. But where is this element in memory? Where does this array start? It starts at whatever memory address gets stored over here in scores. Now scores will then always point to that memory address. So when you want to get back to this array, you don't have to remember each individual memory address. You just have to know where is scores pointing to. We know it points to the very first one, and as soon as we know it points to the first one, we can access any element in this array. Why? Because it's a contiguous block of memory. We know that if we can get to the first one, we can also get to the fourth one at index 3 because it's 0, 1, 2, 3, or 1, 2, 3, fourth element. So that is the key feature of that contiguous block of memory. I know I've been saying it a lot, but contiguous block of memory is what makes arrays work and what makes them really easy to manipulate. That idea of the contiguous block of memory. So how can we reference those individual memory locations within the array? How can we reference the individual elements? Well, here's some very simple examples. So using our scores array. So I want to refer to the 0, 1, 2, so that would be the third element, and I want to store a value of 89 in it. Well, I treat it, as I mentioned, just like you would a normal variable. Scores at index 2 is going to be assigned the value of 89. So that in there, we dump in the value of 89. So we could change that to an 89. That's what that is indicating. The second one, we can say, well, if I want to store in the first the whatever first is pointing to, and it's probably some sort of integer reference. So it could be something like, let's see here, if I could type it in properly, first equals 4. So that would be referring to index at 4. So this would be scores 4, the fifth element, if you will. So we can use the notation simply as we've done with x is assigned x plus 1. We can say scores first is assigned scores first plus 2. We take whatever values in the array at this location, we add 2 to it, and then we assign that value back into the array. We can treat the array elements just like they're regular variables. Even this one right here, if we want to find the average or the mean of these two elements, we say score at 0, whatever's in memory there, plus scores at 1 divided by 2. So it finds the average of those two. We can also just go ahead and access it for display, just like we would a regular variable. We can just do a systemout.println of top and concatenate that with whatever values at score number 5. Arrays themselves, the only magic about them is the fact that it's not one value that you can refer to. You can refer to every element in this array. And that is, again, and I'm going to keep mentioning it, the idea of a contiguous block of memory. Everything in this array belongs to the array. There's no other variable in here from something else in memory. And that is one of, again, the hallmarks of being an array. So a quick referred to here in terms of references. The values held in array are called the array elements. So the things that make up the array. An array stores multiple values of the same type. That is referred to as the element type or as the type of the array. An array itself, that scores value, as we've seen, scores itself is a memory reference, but when referring to the array, we refer to it with the type of that the elements have. So scores is an int array, so that we know that every element is going to be a type int. The element type can be a primitive type or an object reference. A primitive type meaning that it can be a char or a boolean, an int, a double, a float, a long, short, whatever you have, or it could be an object reference. So you could have an array of string, an array of scanners, array of random number generators. An array can store anything. Why can it do that? Well, because we know that a memory reference is actually a type of primitive. It's called a memory address, not a primate, but a primitive. It's a memory address, and a memory address for a 64-bit computer is going to be 8 bytes. So really a memory reference is just another type of integer. So really an array in Java can only store primitive values, because even an object reference is a primitive value, which is a memory location or a memory address. So therefore, arrays themselves can store practically anything. So we can create an array of integers, an array of characters, an array of string object, an array of coins, an array of die, an array of anything. And you can reference that individual value or the individual element because we know exactly where it is in memory. As long as we know where the first one is, and that's the array name, we can refer to any other element in that array. Now the thing is, Java, when you declare an array, it doesn't give the elements any particular value. In the case of a primitive array, it should, because this is the definition of the virtual machine, when you create an array of primitives, it should give every element a value of 0. And if you create an array of objects, every element should get a 0. For objects, it means a null. It should, but there is no guarantee for that. So that we will look at a case where Java creates, or when we create an array, we initialize each element to a known value. And that's very similar to when you declare a regular variable like an integer. We say integer age, and the very first thing we do is we assign it a value of 0. We just do that in the program, therefore the compiler won't have a problem that something isn't initialized, and we know that the value in that array element location also has a known value. In this case, it would be 0. But how do we do this idea of arrays of objects? How do objects themselves get stored? Well, here's where it gets a little tricky. Let's go back to this one. So this one declares an array of integers. So we've got an array of 10 integers, this little block of 10 integers. We know that each integer is 4 bytes, and we now have a block of memory which is 40 bytes big. We know that each one is an integer. So we're going to store the actual value at that memory location, just like we did up here. In the first element, we're going to store 79 and 87 and so on. But what about an array of objects? Keeping in mind that an object itself, to get to it in memory, we first need its reference. So when we create a string object, we say string name is assigned Bob. We know that name doesn't actually store the string. It stores the reference to where it is in memory. So name isn't the string. Name is the reference to the string object. And this is where it gets a little messy. This is actually how it looks in memory. So if you remember, if an array is declared wherein each element is an object, and we talked about the example of an array of strings, each element stores a reference to an object of that type. What is the type of this string of, or this array of strings? Each element is going to have the address of a string. It's going to be a reference. So when we declare string square brackets, Java knows we're going to declare an array here. We're going to call the array names. It's going to be assigned the memory address of this array of strings. But what is going to be of each element? Here's where it gets messy. So names itself is the reference to the array. So we've got 5 elements in the array, 0, 1, 2, 3, 4. Each one is going to be a reference to a string object. And where are string objects in memory? Well, who knows? It's whatever rule the Java virtual machine has for finding a particular location in memory. Now, unlike a contiguous block for arrays, when we declare objects, Java just finds the appropriate memory size, and it finds a little block of memory, and it returns and stores that address here. So this would be very similar to declaring just a regular string, except we now have a block of these references. Where are they again in memory? We don't know. So let's say we eventually start using this array. The first one might refer to a string over here in memory. The second one might refer to one over here. The third one over here. The fourth one down here. And the fifth one way over here in memory. We don't know. We know the array is a contiguous block. But once we start getting these reference variables, these pointers, we don't know where they're going to be. So that's one of the key differences between an array of primitives and an array of memory addresses, which means an array of objects. We don't actually know where these are in memory. Now, the other aspect about it is, what gets stored when we declare that? So if we go back over here, we see that this is an array of integers. And we know integers, by default, should get a value of 0. With this array of objects, what memory address by default is in here? It's not going to create a string object. There's nothing in here that says create string object. It just says create array of string. And we know an array of string, this is actually going to be an array of memory addresses. So what memory addresses are going to be stored in this array? Well, we think it's going to be null, or the equivalent for pointers, which is 0, but we don't know, which means we have to come back to the idea that an array itself is an object that must be instantiated. We have to define every element in this array as well. So even if it's an array of primitives, or in this case an array of objects, we have to give each element a value before we can start using it. So how do we declare these arrays? So we've seen some syntax here, but here's the idea again. We'll do it for scores. So the scores array could be declared as int square brackets. That means we're declaring an array here, not a regular integer. We're going to call this array scores. It's going to be assigned the memory address of a block of memory of 10 integers. So now we know that we have a pointer pointing to this array of integers. Perfect. So when we define the array, this side over here is the declaration to tell us what scores will be. The other side is actually allocating that memory and saying, here's the block of 10 that I found. I'm going to give you the address to the first one, and we're going to refer to it as scores. So scores itself is not the array. Scores is pointing to the first element in the array, which is very, very similar to how objects work. So if we declared a string called name, name would point to the actual string in memory. In this case, scores points to the array itself, which is why in Java, you might hear the term of an array object. And now it's somewhat misleading, but it's only to refer to the fact that scores is not an actual variable. Scores is pointing something similar to an object because it's storing a memory reference. So again, here's another example where we've got an array of double. So we're using the square brackets. We're going to call it discounts, and it's going to be an array of 35 doubles. And now discounts is pointing to that array of 35 doubles. How much memory is that going to eat up? Well, each double is 8 bytes, and that's 35 elements, so that's 280 bytes. Java has to find 280 bytes of memory and then return the address and store that into discounts. So here's some examples of declaring arrays. So the first one is going to define 500 floating points. We don't use float that often, but here's an example where we're actually using it. The second one is going to be called it's going to be of type Boolean, and it's going to be called flags. Now you'll notice the syntax here. It didn't actually declare the array right away. It created the pointer to it, or the reference to a possible array of Booleans. So flags is just a memory reference which Java knows at some point in the future it's going to point to an array of type Boolean. And here later on in the program, and it could be 3 lines lower, it could be 100 lines, it doesn't matter, we're declaring this Boolean array of 20 elements, and we're storing its memory address to flags. So flags again is pointing to the first element in this array. We can also do that with character. So char square bracket is defining an array of characters, and it's going to be 1750 long. The first element is going to get stored back over here to codes. This is possibly how an array could be defined that's going to be stored in a string. So if a string had 1750 characters in it, this might be the array declaration in a string object. So now this string holds all its characters. So that is arrays. So now how can we actually pull values out, or maybe put values into an array? So the simple example, and this is why we almost taught the for loop, why we kept pointing out the for loop in terms of looping structure, is an array is that contiguous block of memory. And each element has a particular index value, so 0, 1, 2, 3. And that goes from the first element, which is always at index 0, up into the last element, which is always n minus 1. So an array of 10 will go from 0 through 9. Those are the index values. A for loop is perfect for that. So let's take a look at the second example here of processing an array called scores, and we're going to display every single score value. So we look at it and we say that for loop here, we're going to start a value I, and I for index. We're going to start it at 0 because everything starts at 0, while I is less than scores.length. And this is something brand new, the length of an array. We'll come back to that in just 1 second. So while I is less than the length of the array, so this would return back for scores, it would return back a value of 10. And we know that the maximum value for the index is going to be 9. So as long as I is less than that length, so as long as I is less than 10, so that should go from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then this loop should stop. Every time through the loop, we're just going to increment I by 1. So we're going to start at 0, then we're going to go to 1, and then 2, all the way up to 9. So this right here is the classic loop through an array for loop. So if you want to loop through an array, this is how you do it. You start I at 0, which is the first index value. I is less than the length of the array, whatever the array name happens to be, I++. This is the easiest way to loop through an array. So that is our loop body. We've got our initialization, we have our condition, and we have our change. And then what happens inside the loop body? Well, systemout.println of scores at I. And we know that I is going to be changing. Every time this loop goes through, I is going to be changing by 1. So it's going to start at 0, 1, and so on. So we're just going to pull out every element at that particular location and display it to the screen. This is the classic way of processing an array. So it's using the idea of flow of control with a loop and the array itself, and we can process every single value. One of the most interesting aspects of this example is we don't know how long the array is. And this is why we have a method here, actually a correction. It's not a method, it's a variable. Every element knows exactly how long it is. Every array knows exactly how long it is. And it's got this value here called length. It's not a method. It's not a method. This is not like the string.length, which is actually a method for a string. An array itself just knows exactly how long it is, and you can pull that length value out. This is treated like a variable. So scores.length is the length of the array scores. We don't know what the value of length is. We don't know if it's 10 or 100 or a million. But as far as this array is concerned, it doesn't care because length has a value. We know how long this array is only because we know that we can pull the value of length out of it. Now, the alternate syntax for processing every single element in the array is this example up here. So we have a for loop again, but it uses slightly different syntax. And what it says is for processing this array, I want to declare a brand new element here called score, and it's going to be every single element in the array called scores. So as the array called scores is processed from the first element to the last element, each element is going to be pointed to by score value here. And then we just display it. This is an iterative type of loop. So this is an iterative loop where we don't specify any particular starting or ending point. But the downside of this syntax is that we can't control which elements we want. We can't say we only want to go from the 4th to the 9th element, nor can we process in reverse. I could start this one. I could start this from starting at the end, the last element, and then go while I is greater than or equal to 0. And then each iteration through the loop, I subtract 1 from I. So I could start from the last element, which of course would be scores.length minus 1. For an array of 10, we know that 9 is the last element. We go while I is greater than or equal to 0. And as it's coming down, we just keep subtracting 1. So this would show us scores in reverse order. But this format over here doesn't let us do that. So this would guarantee that we process every element in the array scores from beginning to end. So it's not as flexible as syntax. In preference, though, I like this format because this is extremely clear as to what's being processed. So let's just make that, let's see, purple. Let's just be a little different here. So that is the syntax that you should be using. A classic for loop that actually starts at the exact spot you want to be and finishes in the exact spot you want to be and displays exactly what you want. So that is a much better way to process an array. So how can we put values into an array? And clearly we have a lot of values that we might want to put into an array. Imagine an array of 1,000 or 2,000 or 10,000 elements. How can you put them in there? Well, if you have a very small array that you want to create, you can actually use an initializer list. And this is only available when you do a declaration. Only at declaration. So you can't use this syntax once the array has been declared. So you can't use this later on. It happens to only be at this particular time. But here's a simple example. We want to declare an array of integers called units. And we're going to store the memory address to where this array is in memory. This syntax right here, using the braces, tells Java, I want to declare an array of a certain size and immediately populate it with values. We don't have to specify the size of the array because the number of values indicate the size. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 elements. So this is going to be declared, if you will, as an int 10. So, but we don't put the size in there. The fact that we've used these braces and indicated all the values immediately creates an array called units, or that will be referred to as units, and populates the first element as 147, the second one is 323, 89, and so on for each element location. We could do that for a char array as well. We could call our array letter grades, so that's going to be the reference. The array itself is created in memory, so it's going to have the first character as an A, B, C, D, E, F, and those will be all the values, and we refer to it as letter grades. So initializer lists are really easy ways to populate an array when you declare it. Now, it doesn't seem to be useful as to why would you ever do this. Well, think of it for letter grades as an example. Letter grades don't seem to change. We're not going to have a letter grade Z or Q. It just doesn't exist. And we know that the first letter grade, the best one, is an A, and then it goes to B and C and so on. So in this case, it sort of makes sense that why don't we just declare them here? And then we can actually use the letter grades, knowing that letter grade at 0 is going to be the A, letter grade at 1 is going to be the B. If we wanted to declare it of strings, because strings are magical, you can actually use that for strings as well. So we could say letter grades. So let's say we didn't want to declare them as character. We wanted to declare them as strings. So we could say A, use the right double quotes here, A, B, and so on. Now, the beautiful thing about this one is, with characters, you couldn't store an A minus, because that is not a character. But here, you could actually do that. You could store an A minus and a B plus, or just a B, because a string can have more than one character. So you can use initialize lists for strings themselves, which is actually pretty cool. So when the initializer list is used, there is no new operator because using the initializer list itself is doing that new operation. It's finding that memory address and returning it. You don't specify size because the number of elements in the initializer list is the size itself. And it can only be used during array declaration. You can't use this quick and dirty way of doing it in any other context. It just does not work. So let's look at a very quick example of using that initializer list and going through a program and seeing what it does. So here's a very, very simple program. It doesn't do any calculations. It says prime numbers, but it doesn't do any calculations. All it's going to do is store the prime numbers into an array of integer. So we're using an initializer list here. It's then going to display the length of the array. It's going to pull out the length value from the array. So it tells us how long it is. It's then going to display each individual array element, which should be the prime numbers. So let's take a look and see what that actually seems like. So here we have Dr. Java, and it's got our prime numbers in there. Let's make this a little bit bigger, just so we can actually see it better. There we go. So we have our array with the prime numbers in there, and we pull out the length, and we're using this alternate syntax, which again I'm not a big fan of, so I'm going to replace this and use the for loop syntax that I much more prefer because it's a lot clearer. So we know that this array is called prime nums, and we're going to be looping while I is less than the length. And we know that each time through, we're going to pull out the appropriate element at position I. So this loops through to the length minus 1. That's all it's doing. It's a counting loop. But within each iteration, the loop body is going to display element at I. So whatever it happens to be. So let's take a look and see what that effect is. So there we go. We know that the array length is 8 and that we're going to display the prime numbers, and we go ahead and display them all. Now it's not that nice in terms of effect, so let's do one more thing at the end. We're just going to do a simple print line, and that will just clean up the output. There we go. So there's our list of prime numbers. Now what if we wanted to increase our primes? Let's say we didn't want to just do 19. We wanted to go a little bit higher. We wanted to add 23, 29, 31, and 37. Now, do I have to go down here and change my for loop? And no, I don't have to do anything else. All I've done is I've made my array bigger, but nothing down here stipulates how many elements are actually in the array. You can see we're just asking for the length, so that should automatically look at this array and say, how long are you? We look at this for loop, and it just loops I from 0 up until the last element, because it's looking at the length again. So we don't have to actually specify anything else. We can just say, go right ahead and display it. So now we should have all those values that we just added without changing anything else of the program. Again, it's this idea of an array. We're just storing a block of contiguous memory locations. The program doesn't need to know exactly how long it is because it can ask the array how long it is. We don't have to hard code in here that this is going to be the value of 30 or 100. We can just ask the array how long it is. For those of you that are in C or C++ background, that have a background in those languages, you'll know that you have to maintain the length separately. Java itself knows how long an array is, so it does have this extra advantage over C and C++. Those are very powerful languages for arrays, but Java has this extra addition that it knows how long an array is. So let's modify this program a little bit, and we're going to play around with some array syntax and see how that looks. So here's a very simple program, and it's just going to go, we're just going to go through some examples of some array syntax. So we have an array here of type integer. We're just going to call it list. You'll see that there's nothing else to this declaration. All we've created is just the reference to a possible array called list. So right now it shouldn't have any values in it. Let's compile it just to show you that this is all the syntax that's required. But let's see if we try and refer to this array. So let's say systemout.println, and I want to show the first element in this array. So clearly I haven't declared it. Java hasn't found this memory. It doesn't have any particular array element values. So let's see what happens if I try and do that. So clearly the compiler has a problem because list itself as an array hasn't been allocated. So list is not pointing to an actual array. So how can you actually have anything in there? So we have to point to an array. Now here's one of the interesting things about an array. It can have one or more elements, or it might not have any. So if we just declare this as an array of size 0, it compiles just right because Java's not checking to see how many elements this array is. So this is an array of length 0. There are no elements in this array. There is no array at element 0. This is an array that points to nothing. Essentially, it's pointing not only to a null, it's pointing to an array. Java tries to go over to memory to find that array, and that array happens to be literally empty, which is possible. There is nothing saying that we might have an array that has nothing in it. We don't have any information yet. We have nothing to store in this array. So it's perfectly valid to compile it. But what happens when we try and run it? We get an error. We get this array index out of bounds. What it means is that we're trying to refer to an element value which does not exist. So let's see that one in just a little bit different context. Instead of using the new, let's use an initializer list. So we'll put 1, 2, 3. So that will be an array of int of size 3. So we know that the index values are going to be 0, 1, 2. So let's try and display the value at index 0. That should be a value of 1. And there's our 1. If we try and do it to the last element, so that is going to be at element 0, 1, 2 actually. 0, 1, 2. So that should give us a value of, if I could type it in right, there we go. We see the value of 3, 0, 1, 2. That is the very last element. But as you just saw, if we try and reach over and grab another element, so this would be the fourth element, if you will, 0, 1, 2, 3. 3 is the index for the fourth element. It compiles just right, but we get that index out of bounds error again. Our array doesn't have an index at position 3. So we see that that's a problem. Now it also happens if you try and use a negative value too. In a way it compiles because Java's not looking to see what the value is. It just sees that that's an integer, which is perfectly fine for an index. But when we try and run it, again, we have an index out of bounds error. And we're reaching outside of the array. This is possibly the most common array error that you'll get. On like 99% of the time, if you have a problem with your array, whether it's functioning and it doesn't seem to be working 100%, or when you run it, you get a runtime error because it's trying to reach out of the array, this is the reason why. You have an index value which is not within the bounds of the array. It's just not there. Now, let's see what happens if we try and declare an array here of, let's say, 5 elements. We're not going to give any particular value to the elements, and let's see what's at the first element. So this is just going to be an array of 5 elements. We don't know what's in there. It compiles just fine, and when we run it, it shows a 0, and that's exactly what we're expecting. Every element in this array is going to have a value of 0 in it. But how could we initialize, and let's say this array list, we wanted every element to have the value of 99 in it. Well, we could use a for loop, and this is probably the only way we could do it. So we could do a for int. We start at the first element, and we go until the end of the array. So that would give us, it's always the length minus 1. That'll be going up to. We're just going to say that list at position I, or at index I, is going to have the value of 99 in it. So now if we wanted to show all those values, we could just do the same thing again. Except in this case, we're going to use the systemout.print statement and show at position I. So we should see 99, well, we should see 99 for every element. And there we go. So every element has a 99 in it. Let's change this up a little bit. So instead of storing a hard value like that, why don't we store in it I plus 1? So that the first element gets a 1, the second element will get a 2, and so on. So 1, 2, 3, 4, 5, which is exactly what we wanted to store. Now our array elements are relatively equal to which element they are. So the first element has a value of 1, the second element has a value of 2. If we wanted to do it in reverse order, the first element has the length minus 1. We could just change that to list length minus 1. And then we also want to remove an I so that the last element, which is going to be, let's see, list length minus 1, that will be 4 minus 0, so that's 4 for the first one. And then the second one will be list length, which is 5 minus 1, which is 4, minus 1, that'll be 3. So it should go 4, 3, 2, 1, 0. So that should be what we have in our element values. 4, 3, 2, 1, 0. Perfect. And you can see how relatively easy it is to manipulate the arrays. The arrays have this contiguous block of memory, which is nice. Let's change that one back to I plus 1 again. And one more feature, which I keep mentioning, is this flexibility in the arrays. Currently, we have an array which only has 5 elements in it. What if we change this over to, say, 100 elements within it? With no change to the rest of the program, now our array has 100 elements in it. So when we run it, we have 100 elements in our array with no change beyond just the size of the array. Beautiful. Now there is one significant limitation of arrays, and this is probably the only downside of arrays. Once you've declared an array can't change size without losing its information. So I can't declare this array called list and make it an array of 200. Let's see what happens. So we know that this syntax here populates the array. We know that this syntax down here displays the array. So what if I wanted to change this array? Once I've populated it with these 100 values, I wanted to change to 200. So I think, well, I'm just going to declare this array and just make it of size 200. That should be fine. I'm just going to head and declare. So let's see what happens now. It's filled with zeros. And it's not just filled with zeros at the end. It's filled with zeros all the way through. What happened? Well, look back at the new. What does new mean? Well, in this case, we declared an array of 100 elements. We returned the address. We stored it to list. We populated that list with 100 values, starting at 1 all the way up to 100. Then we declared another array, and that's the key thing. We declared another array because we said new int 200. So Java went ahead, found in memory a block of contiguous integers, 200 of those. So that gave us 200 integers in memory. We found the address for it, and we returned it and stored it to list. List was previously pointing to this array over here, but now it's pointing to a new array. If we go back over to our lecture notes and look at this syntax here, when we first declared list, it was pointing to that array of 100. Once we did the second declaration, list was pointing to a brand new array of 200 elements. What happened to that previous list of 100 elements? Well, do you remember when we were talking about garbage collection? If nothing is pointing at something, Java will absorb it and return it back for possibly being used for something else. So now we created a brand new list of 100 elements, or 200 elements, that was filled with zeros. We got all these zeros in here. So how could we declare a brand new array, essentially increasing the size of the array, but not lose our data? Well, if you're thinking about why don't we just copy the data from the old array to the new one, you're absolutely right. And that's exactly what we could do. So let's take a look and say we'll call this one list 2. So this is going to be the second list. So it's not going to have anything in it but zeros. And what we're going to do is copy the elements from the old array to the new one before we display the new one. So this will get tricky. So the first step we'll do is copy the elements from list to list 2. Let's use a for loop for that. So we'll go through all the elements from the first array, and what we'll do is for each of those elements, we're going to assign the value from the first array. So what we've got here is process the first array. So it's all the elements, 0 to the length, and this is going to make a copy of element at I from list to list 2. So that should move all the element values from the first list into the second list. So we should have up to 100, and then everything else is 0 after that. Let's take a look and see what that looks like. So let's display the second array. Oh, I guess I should tell it that this is going to be an array. And you saw that we went up to 100, and after that, all the values are 0. Because we didn't say increase or change the values, we only copied all the elements from the first list, and there's only 100 of them. Beautiful. Now, what if we wanted to actually make the effect of the first array? Because the idea here was increasing the size of the first array. So I want everything to still be referenced as list. I don't want list 2. I don't want to introduce a second list. I just want to increase the size of the first list. We started at 100. I want it to be 200. Well, once we've copied all the elements from the old list into the new list, I can point to the new list. Remember, what is list and what are list 2? These are memory references. These are not the actual arrays. So what I've done is I've moved, instead of pointing to the old list of 0x5, it's now pointing to the new list, which could be at 099e. So list went from pointing to the original one, which had 100 values. It's now pointing to the new list, which has 200 values. Now list 2 and list are actually pointing to the same array in memory. So both list 2 and list point to the same array. But the old array in memory of 100, again, it's been garbage collected. So let's take a look at this. So now remember, we're pointing back to list over here. You saw that it's got 200 elements in it again. And if we look at list 2, you'll see that it's also pointing to the 200 elements. So you saw our list go by twice. So there's the list, whoops, there's list 2. And if we go up a little bit higher, we should eventually find the output from the first list reference. There it is. So now we have 2 arrays seemingly, but actually it's 2 references to the same array in memory. Again, one of the cool features of arrays, because it's this block of contiguous memory, and that what we refer to as the array in here as scores is actually just a reference to the array. We can have many references to an array, and that's actually pretty cool. So in the next quick lecture, what we're going to be looking at is processing an array to do things like calculating the total or the average, or maybe populating the values with input from the user. So we'll take a look at manipulating arrays in terms of en masse. We'll look at arrays of, let me look at all the data together and let me process it that way. So we'll see you in the next video.